Okay, so let's review what we learned. We saw the universal model of finite-state computation with our transducers. This is the central object which we want to analyze, both analyze and synthesize. This is what the focus will be. How do we build such object? And we want to build them from specifications. And we said that the semantical, the meaning of this is going to be the traces of T, which is going to be an object of sigma cos delta to omega. And we're going to focus on infinitary languages. But we're going to kind of contrast the theory as we build it to the theory that I think you are familiar with, which is the theory of automata on finitary languages. So we said you start from finite-state automaton. It's non-deterministic automaton, and it looks like this. That is S cross sigma to the S. And this, we can view the same object as an automaton in finite words. Then it accepts if the finite set reaches F, or if we view it as an automaton on infinite words. Thank you. Or if you view it as an automaton on infinite words, except if you visit F on infinite word, the run visits F infinitely often. And as I said, what we want to show is a relationship like this. The traces of T are going to be contained in the language of some automaton, which we view as the specification. Now, one thing that coming down will be, is this is using an automata a convenient way to express this specification? And I will argue that automata in some sense are too low level, and this is not the language that human usually likes to write, and this is where logic will come in as a human level, as a high level language, and then we will try to bridge, and we saw some preview of that in Stefan's lecture yesterday. There is a connection of logic and automata, which I'll get into. But that probably will only get to it tomorrow. What I want to try, first of all, to focus today is on this question. Okay? So today we'll focus on decision problems for automata. And there are really, in some sense, kind of three types of decision problem for automata that we come across all the time. The two most basic one is, given an automaton, is it an interesting object? And what could make an automaton an uninteresting object? It accepts nothing, right? It always says no. So it will be, the language is empty, this is kind of a boring automaton. And that suggests there is another type of a very boring automaton. It always says yes, right? A boring person is, if a person always says yes, always says no, then it's a boring, right? This is boring. The good person, the yes man, right? So these are kind of the two extremes. And of course, here we will have two versions. One is sigma star, is we're looking at finitary languages, and the other one will be sigma to the omega. Okay? Now, let's start with this problem. And again, we have, this has the two versions, that the empty set of no, the empty set is a subset of sigma star, and the empty set is a subset of sigma to the omega. These are two different languages, even though these are questions about the same object, because the same automaton can be viewed as an NFA or as a Bushy automaton. So here is the automaton that we have here. And what's interesting is that the way it was not phrased this way until fairly recently. If you go back to Rabin and Scott, for example, in 1959, they have a theorem that says if an automaton is non-empty, then it accepts a word of the condition is accept a word of fourth length. Anybody remember this result? If an automaton is non-empty, then it accepts a fairly short word. What would be the length of the word? The number of sets in the automaton. That's the way it is phrased there, which I find really, from a modern perspective, somewhat strange, because here is the way I will phrase it. So I will define the graph of this automaton. I will use the set of states as the nodes, and the edges will be E equal all the pair ST, such that T is in row of S and A for some A in sigma. So if one way you can think of an NFA is as an edge label graph, right? You have edges between states, and the labels are the letter denoting the transitions. Delete the labels, and you're left with just with directed graph. Okay, so this is the graph. And now we can rephrase that theorem by Rabin and Scott the following. L of A, the language is non-empty. If and only if, now we're doing automata with finite words, if and only if there is a path in G sub A, and anybody can complete it, the path has to be from what to what? A star state to an accepting state. From S0 to F. Very often, this, instead of one initial set, you have a set of initial sets. This doesn't matter much. Now, the nice thing in phrasing it this way, that if you say there is an automaton is non-empty, if and only if it has an accepted word of length n, it has a word accepted of length n is the number of states, on the face of it, it sounds like, what's the complexity of this condition? There exists a word. You have to guess this word. It sounds like almost like an NP condition. Now, when I phrase it in this way, which is a completely equivalent formulation, what is the complexity of checking for non-emptiness? N log space. This is just graph reachability. This is just graph reachability. Graph reachability is one of the most fundamental algorithms that we have. I mean, if any kind of course you take on algorithms, probably the number of things you do is maybe sorting, and the same thing you should do is reachability, because in all kind of any graph, any network you want to analyze, this is the most fundamental condition that you want to check. Okay? So this is the Rabin-Scott theorem really should be phrased in this way, but at the time people don't think very much algorithmically, but more in terms of expressive power, and therefore this is the right way to but today, from algorithmic point of view, this is the way to think about it, and I think the proof is a kind of an easy exercise, okay? One is, if the automaton is non-empty, there is some word, and that of length n, and that word must take you from S0 to F. And if there is such a path, there were some labels on the path. Just take the labels on the path, and that will give you the word in the language. But now I want to modify this to these questions. I want to rephrase this lemma to this question. And the condition is now that you have, remember, now we are looking for an infinite word accepted. And an infinite word is accepted if it takes us infinitely often through F. So first of all, if you need to go infinitely often through F, what does it imply? You have to go to F at least. I can paraphrase a Chinese proverb, right? A journey of infinitely many steps start with one step, okay? So you have to be able to get to F. Otherwise, you're not going to be able to go infinitely often through F. And so in some sense, this is still required. You still have to go from S0 to F. Now, the next point is, remember, we use the pigeonhole principle to argue that there must be one particular state in F that is repeated infinitely often. What does it tell us about this state? You have to be able to go from this state back to the same state. Now, this would not be true if we are not dealing with finite-state automata. If you're reasoning, for example, about infinite behavior of infinite-set programs, then you could then this condition does not hold. There are other ways you need to think about it differently. Because this is finite state, then now the other lemma, this is lemma 1, and I will here denoted this is a subset of sigma star. And lemma 2 would say that L of A is not empty, viewed as a subset of sigma to the omega, if and only if there is a path in G sub A from S0 to some T in F and a path from T to T. And so if here we are just looking for a path from one point to another point, here we are looking for something of this shape. So what are you seeing here? People see two different things. Some people see lollipop, and some other people see lasso. So this has become known as the lasso test. We're looking for a lasso. Now clearly this you can do in n-log space, which is also in polynomial time. What about this? Finding a lasso. What should be the complexity of finding a lasso? Again, n-log space, because you guess this path, and you have to guess a point. You say, okay, this is the point of looping, and then you guess the path that comes back to this point. So from complexity theoretic point of view, they are the same. But now let's think in terms of real algorithms. Okay? So if you have to implement lemma 1, which algorithm would you use for that? This is undergraduate stuff, guys. You need to know that stuff. What algorithm would you use to find existence of a path from start to accepting states? Spell it out because B and D sound the same. DFS. Depth first search? Okay. Can you use breadth first search? Yeah, you can use both, right? This is important. You can use both. Here you have to find cycles. When you come to finding cycles in a graph, breadth first search is no good for finding cycles. So here you have to use depth first search to find cycles. Why does it matter? Anybody heard of symbolic model checking? Okay, in symbolic model checking, we're dealing with what happens when the graph or the automata that we are dealing with are extremely large. I mean, the famous number is what, 10 to the 20 states, which is what, 100 trillion, large number of states, which is roughly 10 to the 2 to the 64. It's not that much. It's just reasoning about one 64-bit register, okay? The state space goes very, very quickly when you think about such systems. So the observation going back to about 20 years ago, that when we try to do explicit algorithms on graphs, at the time, which is 20 years ago, typical implementation would max out with about million states. I don't know today, but maybe you can deal through it, but it's doubtful that we can deal again, maybe with 10 million states. Maybe I don't think you can do much more than if it's still maybe 10 million states. After that, algorithms, the graphs become too big to really do explicitly. Just the way you think about graph nodes going from a node to node. And then we get into something, I won't get really in detail into that, but you get into what we call symbolic algorithm, in which you describe the graph symbolically by means of formulas or BDDs, and you reason symbolically about this graph. These are called implicit or symbolic algorithms. It turns out in symbolic algorithm are very suitable for breadth-first search, because you can take a set of states and you can calculate symbolically what is the set of all successor states. But depth-first search algorithms are kind of very explicit. They're kind of a node at a time. You take a node, you go deep, and so symbolic, it's much more difficult to implement depth-first search algorithms. So it makes a big difference in practice. Even though we say, oh, it's n-log space, it should be the same. When you get to practical algorithm, huge difference between reasoning about finite and reasoning about infinite traces. So even something so simple that we don't see the difference in the complexity, in practice, there is a lot of difference. So this is the old cliche, what's the difference between theory and practice? In theory, they're not that different, but in practice, they're very different. Okay? So just remember that. So this is the first algorithm that we do is non-emptiness. So non-emptiness is really an easy problem. Right? It's the basic, you can think of it as the basic satisfiability questions for automata. Satisfiability of a formula that does have any satisfying assignment. This is the satisfiability question for automata, and it's an easy question. The other problem we want to deal with was universality. Now, universality, we have to find out whether the automaton accepts all words. And partly what makes it even more difficult, this is a non-deterministic automaton. So for every word, there has to be some accepting run. And it's not clear how you do it directly. So we actually don't have a direct algorithm for it. We're going to reason indirectly. We're going to the classical mathematical technique. We want to reduce something to something else that we already know how to solve. So we just saw how to solve the emptiness problem or the non-emptiness problem. So universality translates to emptiness if we can build this object. And of course, what we want from this object is that it will be sigma star minus L of A. And this is called complementation. And if we could do that, if we could build this automaton, then we have solved the problem, right? So if you want to deal with universality, that's how you do it. You complement, or if you think about it differently, I can do it this way, which means that what I will be looking for, if I find a witness here, then it becomes a counterexample here, right? The satisfying assignment of one becomes counterexample for the other, and that's why you can think of it as the counterexample method. And the counterexample method is very often the way we solve many automata-theoretic problems. We are looking for counterexample, because looking for something that is constructive. You want to find either a witness or a counterexample. These are both constructive ways of trying to solve problems. Now, if the automaton were deterministic, so it's a total function, then complementation would have been very easy, right? How would we complement a deterministic automaton? Just complement a set of accepting states. Just switch if you have at the end, think of it as taking a circuit, a machine, and add one negation gate at the exit, just to flip the decision. So that's easy. So on the other hand, the problem when we have non-determinism is that there is this quantifier. We are quantifying over the runs. That means if you want to complement, the existential quantifier becomes a universal quantifier. Now we will see a bit later on, right now our automata do not have existential quantifier. We only allow existential quantifier. And we will see a bit later on that there might be a reason to add universal quantifiers to automata. But right now, they don't have it. So essentially, if this is an NFA, then we need to, the only way we can complement is to first determinize. So this is how typically we think of complementation. We determinize. We're going to determinize it, and then we're going to complement it. Again, here I'm going quickly because I assume that you have seen this material before. And the way you determinize it is the so-called the subset construction. And so the intuitive idea is that you can think of a run with non-deterministic machine as a tree. You start in S0, and then you read the first letter, and there are a few possibilities. And then you read A1, and again, there are a few possibilities. And at the end, we get all the leaves, and the requirement to acceptance is, if you think in terms of the tree, what is the requirement for acceptance in terms of the leaves? What should we see at the leaves? At least one accepting state. Now, suppose at some point there is a state here, S, and the state appear in another place. Then what will be, now there are subtrees here and subtrees here, but since at each point we take all the children, all the successors, if you see S here and here, because you're reading the same word, you're going to see the same subtrees. And so there's really no need to keep this full tree. We can instead, when we have that you visit S twice, you can merge and do this and get a DAG. And the difference is that the tree has width that keeps growing. And the DAG is always going to be, the width of the DAG is always going to be the number of states. And in fact, all that matters is always just what are the states in that level of the DAG, and in the final, when we get to the leaves, we want to know that it contains an accepting state. And this gives us the so-called subset construction. So the state space become 2 to the S. The accepting states are all the sets that contain at least one accepting states. And rho sub D is going to be a function, rho sub D of P and A is going to be a union over all S in P of rho S A. Okay? So this is what we call collection semantics. You have a set of states P, and you read the letter A. You look at all the states in P, you apply the transition function, and you take a union of all the possibilities. This is the subset construction, and you get a deterministic automaton. And because it's deterministic, we know how to complement it. So, in fact, all we have to do here, it will be to complement it here. Once I will do this, I have complemented it. So now we want to check, what do we have to do? We have to take this complementary automaton, and we have to check this automaton for non-emptiness. What's the complexity? Why P space? Okay. So the way I described it is going to be exponential time, because I said first complement, which is going to be an exponential blow-up, and then look for an accepting path in a complementary automaton. But then you pay the price that this is exponential blow-up. Okay? And what was said before, what was said here was that we can do the construction of this complementary automaton on the fly. That is, we're really searching for a path, and we know at each state how to find other successor states. So we can search for a path in this automaton without ever building it explicitly by starting from some initial state, from the initial state, guessing one successor state, which is a set of, for this very often we call them macro states. These are big states, and which are a set of little states, and then guessing the next one. This is an algorithm in NP space, non-deterministic space, but this is equivalent to deterministic space. Okay? In practice, this it's very nice to say this is in P space. In practice, it's going to be a terrible algorithm. In practice, you build a dumb thing, and then you solve for non-emptiness. Okay? But it's nice to say the complexity is in P space. But in particular, the Savage theorem that tells us that that NP space is equal to P space, if you think the algorithm that it gives you is absolutely horrible algorithm. So don't try this at home. Okay? So this is actually all fairly easy. Okay? So now we want to do the same thing for automata on infinite words. So we said, okay. So far everything extended fairly easily. So now we have to figure out, first of all, how to do complementation on automata for Bushy automata. Okay? And so it seems kind of you should do the same thing, and that's what some people in fact have done and published. Let's do the kind of the same thing. Should work. Here are two automata. This is a very simple. We have the alphabet is just one letter, 0. So there is only one word, infinitary word, right? 0 to the omega. That's it. Does this automaton accept 0 to the omega? Yes, it does. Doesn't matter how you go, but go here and just loop forever here. How about this automaton? Does it accept 0 to the omega? Why not? What are your options? If you go here, you can stay here forever, but then you're not accepting. You really want to go to the promised land, but once you go there, you die. Okay? So you're stuck. You cannot accept. Now let's call this. Let's call it S and T. S and T. And let's do now the subsequent construction. Let's see what happens in subsequent construction, right? We start with the state S, and then what is the successor state to S? You take all the possible transitions. So the successor state here is ST, and the successor state of ST is ST. Now let's do it here. You start with S, and then 0 takes you to ST, and the successor state to ST is, from S you go to S and to T, so go back. So these two automata, the subconstruction obliterates the difference between these two automata. And the point is that here you can start to see that there is essential difference between automata on finite world and automata on infinite world. On finite world, the only matters is what happens in the end, right? This is a classic case. The mean justifies the end. You only care about the end here, okay? But for Bushy automata, that's not the case. It's all about the means. What have you done? Not are you rich at the end of your life, what have you done along your life, okay? And substance construction forgets history. It only cares about what happens. It doesn't really remember the path that went through this. So we lost the difference between these two things. In fact, we should already realize that the strategy that we use for NFA of complementing, which is first determinize and then complement, should be doomed for Bushy automata and should already follow from what I told you yesterday. Why? Because NBA are more expressive than DBA. So we cannot just take NBA, determinize them to DBA, and then do some complementation. Not only that, even if they are deterministic, it's not clear. Even let's take even a deterministic Bushy automaton, just to see why this is. Imagine this is a Bushy automaton. Oh, it's over there, it's written there. Imagine this is the deterministic Bushy automaton. I cannot complement it by just complementing the accepting states. It's not the same thing. Not to visit a states infinitely often is not the same as visiting an infinite and the complementary set infinitely often, because you could visit both infinitely often. So this difficulty was faced by Bushy in 1960. So the part of the history is that the questions about infinite words or about reasoning about infinite traces are raised in 1957 by Alonzo Church. He starts thinking about circuits, and he proposes this infinitary semantic for circuits. It goes to Church in 1957. And he posed some questions. His paper is mostly about posing questions. And Bushy is the one that takes on these questions. And Bushy comes up with the idea that we need to extend the work of Rabin and Scott on automata on finite words to automata on infinite words. And first, we need to solve the non-emptiness problem. Okay, this is not so difficult. It's not exactly that Bushy used DFS to do that. There was no DFS at the time. But essentially, kind of the lasso test was something that essentially you can find it in Bushy's work. But then he was facing the problem of complementation. And so what's amazing about the complementation problem for Bushy automata is that this is by now 1960s. So we're talking about more than 50 years of research. And it's an incredibly simple problem to state, right? I could have started by just, here is a Bushy automaton. You know, you build an automaton, accept the complement. And in some sense, you can say the problem was already solved by Bushy in 1960, but this is still very much a live research problem, okay? So Bushy publishes, his paper comes out, he gives a talk in 1960, and the paper comes out in 1962. And in 1962, you published this, you didn't have to do a complexity analysis. The concept did not exist yet. And we'll see other works the same way, that people publish construction and it didn't occur to them, they have to analyze the phrase, what is the complexity of your construction? The standard question at the end of the talk that one could ask did not exist then. You couldn't ask this question at the end of a talk. So you go to Bushy and there is no analysis. What is the complexity? It's not a topic. And it's not easy to do this analysis because the paper is incredibly hard to read. But as best as we can tell, the complexity was doubly exponential. If you implement it in a straightforward way, the complexity is doubly exponential. But that question did not come up until about 25 years later, in the mid-80s. Questions start coming up. Okay, what is the complexity? Because these people start actually implementing these things. So I'll tell you an interesting anecdote. So there is an Israeli computer scientist, mathematician by the name of Jacob Shweka. And he was a student of Michael Rabin. And Michael Rabin did the fundamental work on automata on infinite trees in '69, I think. He was his student. And they worked on automata on infinite words. Published a paper, I think, one of his papers appeared in 1974, 75. He graduated, and then he switched areas completely. He went to information retrieval. left automata theory completely behind him. I took courses from him both as an undergraduate as graduate students. And in the 2000s, he retired, and there was a workshop in his honor. And I was invited to give a talk in the workshop. And then after that, there was a dinner. And he says, I have to ask you a question, something that I was never able to figure out. He said, when I published my paper, the reaction to my paper was a thundering silence. Just you publish a paper and nothing happens. It's like you give a talk, at the end of the talk, any questions? Total silence. Nobody has any questions. Okay? Now, in the 1980s, there was no web. There was, how do you, if you get access, you want a copy of a paper, and it's not in your library. Anybody know what you used to do? I think anybody is old enough to remember that. So, you write to the person, but it was so standard you write to the person, there were standard postcards were printed of requests for articles. Instead of having to write, dear so-and-so, it was completely standardized. So first of all, when you publish a paper, the publisher gave you 50 gratis copies of reprints. You got 50 copies, and then there were completely standardized postcards. And you just had to, this was all the nice words, dear so-and-so, I'm interested in your beautiful work on, and you just have to fill in the title and what paper it was. And so he said, for about 10 years, I hear absolutely nothing. And then the postcards start to arrive. And first it's a drip, then it becomes a flood, and I run out of my 50 copies, and I have to go and make on my own expense more copies. Everybody wants copies of the paper. And I could never figure out what happened. So it took 10 years. So the story was that really nobody cared about the paper at the time. But about a decade later, it was discovered, the relevance of verification was discovered, and his paper started getting citation, and then people wanted to read it, and they started. It's a beautiful paper. I still encourage people to read that paper from 1975. So it turns out that Bush's construction is on, as far as we can tell, if you implement it naively, it's doubly exponential. But you can implement it more, essentially the same ideas can be implemented more carefully, and then you can implement it with a construction of 2 to the n square. So this is an exponential, but with a quadratic exponent. I'll come back to it later. I don't know whether I'll be able in this course to go actually through a complementation construction, but I will see if we can do it towards the end. But one of the things is that over the years it was improved to 2 to the n log n. And this we know now is optimal. But there's still, what is a good construction for implementation is still very much an active research area. So this is by now a saga that is approaching almost 60 years, and it's still very much alive research questions. And the point is that now you have to do what we call direct complementation. You cannot do the indirect one, which is determinize first and then complement. You have to complement from non-deterministic to non-deterministic. Okay, so this is part of the challenge here. And to do that, first of all, you have to essentially get into this, again, going to the run trees. I talked to you about the run trees. Now, these are infinite run trees. And now you need to develop a deeper mathematical analysis. What are the mathematical properties of these run trees before you can do this complementation? So we talked about two decision problem. One was the non-emptiness problem. The other one was the universality problem. But really, the thing that motivated from us at the beginning, which has something in common to both of them, was something in between. This is the containment problem, right? Because we said we have one automaton that captures all the traces of the transducer, and one automaton describes the upper bound, all the traces that we want to allow, and we want to check for this containment. And so, again, think about it. You have to reason about every word here has to be accepted here. How do you do this kind of reasoning? And we are much better at looking for concrete object, for witnesses, or for counterexample. So we're going to pursue the counterexample method here. So I want to translate this into a problem of finding just one witness. So what's the witness I want to find? What would be, how do I reduce this problem, which is of universal nature, to something of existential nature? How do you translate universal quantifier to existential quantifier? Negation. You negate the problem. So what happens if I said I want not of this to happen? What is the negation of that? The negation of that is that L of A intersect the complement of L of B has to be non-empty. Right? It means the counterexample with something that A accepts and B rejects. Now, this is a set. How do I complement this set? I have to complement the automaton. So if I can do complementation, and what else I need to be able to do? I need to be able to do the intersection. Okay? So that's the other thing that I need to be able to do. I need to be able to do intersection. So let's see about how we can do intersection. So one of the things that we have about, let's say for automaton finite words, these are regular languages. Regular languages enjoy many closure properties. What are the closure properties that we know they enjoy? Regular languages, they have many closure properties, but the most basic ones are, speak up. You, with the purple, Mr. Purple. You're Mr. Purple, yes, speak up. Closed under? Complementation. First of all, the standard Boolean operation, and we talked about complementation. And union is easy for non-deterministic automata because you just have to guess which automaton to run. But intersection is less trivial. So if I have A1 equal sigma S1, S01, Pro1, F1, and A2 equals sigma S1, S2, S02, Pro2, and F2. And now we take the intersection and we implement it via the product operation. And we have sigma. Again, this is stuff that you should have seen in undergraduate course. Sigma S1 cross S2, S01, S02, rho 1 cross rho 2, F1 cross F2. And I just need to define the product on the transition function, rho 1 cross rho 2 of S1, S2 is going to be rho 1 of S1, A. So letter A cross rho 2, S2A. Just two automata, you just run them in parallel essentially. This is the cross product. Essentially, you can think of the parallel construction. And the key thing is that at the end, both have to reach acceptance. Now, this is for automata on finite words. Now, I want to do the same thing because I need to do the same thing. I need to implement the intersection operation here. So now, assuming that these two are Bushy automata. So I can take, okay, I can kind of do the same product and run both in parallel. But the tricky part now will be to define the acceptance condition. And why is just taking the product the wrong thing to do?
Because it could just have infinitely many accepting states of one automaton, and not we want them to have infinitely many of both of them.
Well, the problem is that I'm forcing them to synchronize it. They have to accept accepting states at the same point, and there is no reason to do that. There are two tracks. You can think of them as two tracks. On each tracks, I need to accept infinitely often. But this will be okay. If you do that, you will be visiting each one infinitely often, but you're forcing them to visit at the same time, while we need something much looser. We need each track to have infinitely many things. So you see now that again, that Bushy automata are sensitive to history. While automata on finite words, the history doesn't matter. You can do whatever you want as long as you have victory at the end. Okay, this is the kind of the end justifies the mean, and Bushy automata have to be moral automata, right? They have to behave well infinitely often along their life. And so suddenly, even little things like again, union would be trivial for Bushy automata because they're non-deterministic. So again, all you have to do is just guess at the beginning which one to use. But even intersection is already problematic. Okay? Now, one way to try to overcome this and so we run into this problem before that. Maybe the problem is that these Bushy automata are, the acceptance condition is too strict. Maybe we need more general acceptance condition. Maybe just accept condition that Bushy defined. We saw, for example, it's too limited to be, it's not strong enough to allow for determinization. It's one example of this weakness of this condition. And we will see later there are conditions that are stronger and they have the ability that, in particular, that you can determinize within that condition. But not for Bushy automata. So here is a minimum attempt to generalize them. And these are called generalized Bushy automata. And here, this would be the condition. But instead of having one set of accepting states, you have a tuple of sets of accepting states. And now the condition is that Iran is accepting if inf of R intersect Fi is not empty for I equal 1 to K. So you have to visit this one infinitely often, and this one infinitely often, and this one infinitely often. And then if we do that, then we should be able to do intersection. What should be here the acceptance condition? Remember, I want each tract should visit accepting states infinitely often. So what generalized Bushy condition can I put here to make that happen? All right. So you have two conditions. Here you say you have to visit F1 infinitely often. I don't care what happens in the other track. And this says you have to visit the second track in the second set infinitely often, and I don't care what happens in the first track. So one question is, okay, we've generalized this. Is it really more powerful? Are you just clearing your throat, or are you trying to say something? Okay. So very often we are facing this kind of, so what happened is for automata on finite words, there's essentially, it's very robust. There is one standard notion of acceptance, and that's pretty much it. The final set will be accepting. You can think of other notions, but they're not very natural, and there is not much study of what happened with other conditions. This is not the case for automata on finite words. There are many different acceptance conditions, and one of the things that you want to study is the relationship with acceptance conditions. And one question will be, do they add expressive power? So the answer is, in this case, Bushy automata already defined a class of what we call omega regular languages. And we will see other characterization. In particular, we'll see a logical characterization of this class. So it's actually a very robust class. But we can still study different acceptance conditions and see how we go between them. And one thing you could ask, what is the succinctness? What is if you do the translation, what is the complexity blow-up of these translations? So the first condition we want to check, okay, is this really, we use this condition, what happened? Can we go back to Bushy automata? So I want to get rid of this generalized condition. I want to go back to Bushy automata. Now I have these two tracks that I need to watch. And but I want to be able to reduce it at the end to one set of accepting states. Now, the beauty of infinitely often is that you have the ability to ignore very long stretches, arbitrarily long stretches. You can just ignore, right? You can look at if you're trying to see that something will happen infinitely often, if you ignore a finite stretch, it's not going to change the outcome. This is infinite is very qualitative in some sense. It's very robust. You can take an infinite set and drop any finite set, and you're still left with an infinite set. So if I have to monitor these two tracks, what will be, just think of yourself as the monitor. How would you monitor the two tracks, both with acceptance infinitely often?
It infinitely often happens that you visit F1, then F2.
So monitor first one track until it reaches an accepting state, right? And what will you do at that point? Switch to the other track and wait till you get an accepting state, and then go back. So you just have to go back and forth infinitely often, right? So that's what we have to do this. So if we have to go back and forth infinitely often, that means that there is another component of the state now. There is a new component to the state, right? What is that component? Which track am I monitoring? Okay? So let me first of all just to make life a bit easier, let me change my terminology here. I want to call them A0 and A1. It's going to be a bit easier. So this suggests that we need something else, another version of it, A0 cross A1. What's going to be sigma S0 cross S1. But I need another bit that tells me which track I'm monitoring. Right? So I need to double the state space. I'm adding one bit. Adding one bit that tells me how to which one I'm monitoring. Okay, so now I need to take row 0 cross row 1, and I want to apply it to, again, a pair of states. Let's call them S and T. S and T and the letter A. Now here I just took the cross product, but now I have to be a bit more thoughtful. So I should go to S prime, T prime. I'm sorry, there has to be another here. Of course, there is a third element, which is the indicator. And let's just, first of all, I have to go to S and T prime. I need to be that S and T, S prime is in row 0 of S and A, and T prime is in row 1 of T and A. But I need to update the indicator. So what should be the rules about updating the indicator?
If you see an accepting state of the track that your indicator indicates, then you change it, otherwise.
So what do we say? So I0 and maybe we need to call it so let's write some rule. So if I equals 0 and S is in F0, then I prime would be what? But if S is not in F0, then then I prime equal 1, and otherwise I prime equals 0. So you flip. And similarly, we'll see if it works. Similarly, you have to do if I is 0, if I is 1, and T is in F1, then you flip. Otherwise, you keep it there. So this is the flipping strategy. It's very simple. Now we have to define the acceptance condition. Now I want just a Bushey condition. This will be one set of states, right? F1 or F0, I think, cross S1. What about the value of the tag?
0.
Okay, let's see if it works. So what does it mean each time? What happens when you visit F0 and the tag is 0? What do you know happens? The tag switches to 1, right? Can it get stuck at 1? No, because it has to come back to 0 to accept. And the only way it will come back to 0, if at some point on the second track, you will visit an accepting state. So by saying that you visit here and also, but you come here with the state 0, we know that when that happens, you always go to the other track and you must come back to the same track. So generally, if the generalized Bushey automaton has k conditions, k sets, you'll have to blow the state space by a factor of k. Now the interesting question is we still don't know whether this is a good idea. And what I mean by that, we could have instead designed, instead of saying let's go back to Bushey automaton, we could have said let's work with generalized Bushey automata, but instead what should we modify? The non-emptiness algorithm, instead of having a simple lasso test, we could ask for a lasso that visits, that instead of just goes through one, we ask for a lasso that visits all of them. We can try to modify the algorithm. It's still not so clear which one is a better algorithmic approach to do that. The evidence goes sometimes this one, sometimes another one. So this is a case where I would say theoretically this is the elegant way to do that, but it's not always clear that the most elegant construction necessarily always give you the best algorithm. So now we have kind of the basic idea of verification. So the basic idea of verification is that we have a transducer, and we're going to look at it as a very simple Bushey automaton where all the sets are deterministic and all the sets are accepting. Essentially, it just generates a set of possible traces. And we want to compare this set of traces to some specification giving us by another automaton. We want to check for that containment. And the way we'll do that is by taking the product of A and the complementary automaton and checking for non-emptiness. And we have to be able to do complementation, and we have to be able to do product. If we can do all of this, then we have it. As I pointed out, this is a non-trivial thing to do. And so the fact that it's a non-trivial to do complementation, there are kind of two ways we can address it. One way is to say, you know what, instead of being positive, maybe it's better to be negative. And that is to say, instead of the specifier describing good behaviors, maybe the specifier should specify bad behaviors. In fact, most of us tend to be more negative. You go to a lecture, and then after the lecture, you go to the coffee break, and you say, you understand what he said about that? No, it was not clear at all. You know, criticizing, we're all very good critics, okay? This is the human conditions, right? They sit around people must have sat around the bonfire in the cave and complained, the mammoths today are not as big as the mammoths of our parents, you know? So, and in fact, very often when we talk about system, we say, what should not happen, okay? And so maybe we should never specify this. Maybe we should just start by specifying directly bad behaviors, and then there's no complementation. Specify bad behaviors, and then all we have to do is to do product, and product we see is just, this is a nice little twist, but it's not that difficult. We do product, and we check for non-emptiness. This is one way to approach it. The other way to approach it is perhaps we made a mistake in using a formalism that fundamentally is asymmetric, and therefore it's very difficult to complement it. So non-deterministic automata are asymmetric, right? They have existential non-determinism. So as soon as you try to complement them, you have to use universal, some kind of form, what people call universal non-determinism. It's become much more difficult. There's other formalism where complementation is very, very easy. So we saw one such formalism in which complementation is very easy are the deterministic automata, but they are less powerful here. They are just not good enough. What other formalism is very, very easy to complement? Even simpler. Logic. How do you complement in logic? You add one symbol. You say not. Right? Logic is very easy to complement. Okay? You can say something in logic. You can easily say the opposite. Okay? I think this is a strategy of kind of low-grade debate. Somebody says something and you say not. Okay? This is just an easy way to debate someone. Whatever they say, you say not. So logic is another way to do that. So let's start to think about another way we can talk about describing what we want to describe the same object. We want to describe traces, finite or infinite, but now we want to use logic to do that. So let's start. Well, now we're going to start the logical approach, and first we will start to use finite, and then we'll go to infinite. So a better way, in fact, even the people who invented parameterized complexity say today that it was the wrong word, the wrong term to do that. That the right term to do that was multivariate complexity analysis. Partly because if you look, for example, at what Stefan talked about, if you look at in databases, the input has you have two types of inputs, right? You have a query and you have a database. It's not clear that you can say one is a parameter. It's not clear exactly why it's a parameter. You have two inputs to the problem, and the complexity depends very differently on the two inputs. So if you go back to think about, for example, we'll see it even more when we talk about when we use logic for specification. Okay? So typically, if you ask, okay, let's go with the database and queries. How big is the query? Anybody has ever written a query here, SQL query? Okay, how big was it?
It was a few lines, but compared to the database.
A few lines, okay? I mean, I would generally say that the queries are about this big, okay? We can't do something much bigger than that. So queries are generally small, and databases are typically large.
Is it still true? I mean, with automatic generated queries, you get from...
How big? Okay.
No, it's a question. I don't know.
Maybe a whole page, but you know, nobody will handle a query that is of size of gigabyte. Okay, it just won't happen. There are always orders of magnitude smaller. Even automatically generated query, people says, okay. When people write joins, they're talking about a 5-way join at most, and when you write with views and automatic generated queries, I get 50-way joins. But this is still incredibly smaller compared to the database. And so it makes sense when you do the analysis to say, well, there are two factors to the problem, and they influence the complexity in a very, very different way. So this is really the essential insight. After that, you can go into say, okay, we think one will be small, much smaller, and therefore we are willing to tolerate maybe an exponential factor in the small, but not in the large. This is kind of the motivation. And so when you talk about the complexity here, I said, look, it's a containment problem, right? And again, this is the implementation, and this is the specification. So we have two different variables that are two. This is a multivariate analysis. And remember what we had to do, right? We had to take T cross A bar and check for non-emptiness. So imagine that this is fixed. What is the complexity here in T? It would just, remember, this was just non-emptiness test. This is just finding a path or a lasso. So this is going to be essentially n-log space, or polynomial time, if you want. Here, imagine that this is fixed. Here we have to complement this one. And this we know this is p-space. In fact, it's p-space complete. So here we talk mostly about upper bound, but we have seen here that universality was already commented. This was in p-space. In fact, it's a p-space complete. In fact, it is a more natural problem. Usually when you think of p-space complete, people think of QBF. But to prove actually NP completeness of QBF is harder work. Because you have to take a p-space Turing machine and somehow reduce it to some alternating structure of QBF. And so it's actually, you need some tricks to do the encoding. It's not an obvious thing. While to use automata universality to reduce p-space to universality, it's a completely straightforward reduction, essentially. Okay, so it's a much, much easier reduction. So it is the p-space complete problem. So just like in databases, things work out just the right way here. Why? Because this is usually very big. This is implementation. This is your laptop, okay? This has 100,000 or millions of variables. This is astronomically large. Okay, it's so large we cannot even linear complexity is not good enough. But the point is, we get nice complexity in the big thing, and we get higher complexity in something we expect to be smaller. So magically things work just kind of the right way here. Okay? We get complexity-wise, we get linear complexity in this and exponential in this. So the question, what is the complexity? The answer is, well, formally it's p-space complete, but really when you look more in a more refined way, you got a more refined picture, and actually it's a decent picture. And it was used early on to justify exponential algorithms to say, look, they're exponential in the small variable. They're linear in the large variable. So we can tolerate it here. Of course, if we had exponential algorithm here, we couldn't tolerate them here. Okay, now we want to go to think of another formalism. And we want to use logic as our specification language. And one motivation that I used was that logic is, first of all, it has a nice property that it's very easy to complement logic. But more fundamentally, if you think about it, finite automata are very low-level formalism. This is electrical engineering view of the world, right? You have states and you change states. That's how you build, in fact, even electrical engineers don't design system today like that, right? They design in a higher level and use their synthesis tool that really reduce everything to the low level. So we want higher level. We want that there is a very fundamental principle in computer science, which is that we want high level languages for humans and low level languages for machines. And what do we do? How do we bridge the gap between high level and low level? Compiler, right? Now this is an idea that today seems obvious, wasn't always obvious. So I'll tell you two stories. One I read, one I heard. So the first story that I read was about this, and the both have to do with von Neumann. So the first story that I read was that the concept of assembler was invented in Princeton by one of von Neumann's students. Before that, people would write programs in binary or octal. Octal was high level, okay? Hexadecimal was a huge improvement even over octal, right? That's how they write initially programs, and it was very tedious. You have to remember the name of the registers and the opcodes for the octal opcode for every instructions. And one of the students got tired of doing this and invented the idea of using opcodes in language, add, load, things like that, and using symbolic names for registers and writing the whole thing in assembler language. And then, not clear, I never understood why it's called assembler, but it's some kind of a low-level compiler, but translating this to machine language. He wrote a program, he was very pleased of himself. He went to von Neumann to tell him about it. And von Neumann said, you are wasting precious computer times on clerical tasks that every human can do. Okay? This is what von Neumann said about it. You should save, using computer time to computing like ballistic trajectories. That's good use of computer time. Clerical tasks should be done by human. Now, the story that I heard from John Bacchus. John Bacchus is the inventor of Fortran, and I had the privilege of, amazingly, of being his manager at IBM, something that still I think is just absolutely mind-blowing. And he told me that when they were working in the early 50s on the Fortran compiler, von Neumann came to visit. Von Neumann died in 56 or something like that. This was earlier 50s. He died from cancer. And von Neumann at that point was God, okay? God is coming to visit, and of course, if God is coming to visit your lab, you want to show your God what you're doing in your lab, and you hope that God will say, nice work, right? Von Neumann was just incredibly underwhelmed by what they were doing. He's listening. He finally said, why are you doing this? Not a good question to hear from God, okay? And so they said, look, I mean, writing even in assembler is difficult, we want to increase productivity, it's just how to program in low-level languages. He said, nonsense, just give it to a graduate student. So the principle is give high-level languages for humans and translate it to low-level language. And to me, it's actually quite an amazing historical coincidence that in the 1950s, where you have people who are, John Bacchus and, all the people developing programming languages coming up with the concept of compiler, and exactly at the same time, logicians are coming up with exactly the same concept of translation from logic to automata. It's cosmic coincidence. I don't think they were inspired. It just somehow the same idea occurred to them. You can go from high level to low level. So let's take a word. Is this a word in Polish also? Okay, excuse me for misspelling it. Abracadabra, okay. This is a word. And I want to use logic to specify this. So how can I use logic to specify words? So we are familiar with using, for example, regular expressions to specify languages. But how can you use logic to specify words? So we are a bit more fundamental than that. To specify logic is about structures. So this is actually, if you go back to when maybe one of the very early texts, what we call in modern mathematical logic, you would go to Frege in 1870 something, Begriffsschrift, language for concept. But when Frege defined logic, the distinction between syntax and semantics was not very clear yet. In fact, the distinction between even the language in which you talk about object and the object themselves, there was not a clear distinction. This distinction came where? The clear distinction between syntax and semantics was developed, maybe not in this room, but somewhere around here in another room with less nicer chairs. There's a story there that maybe Nikolai will tell at some point. So this clear distinction, and the funny thing is that this distinction, Tarski is the one that came up with a very clear distinction between syntax and semantics, which today is very, very fundamental to logic. Not everybody likes it. Gerard refers to it as the Tarskian travesty. Not just didn't like travesty, you know. This is Gerard. But Tarski came up with the definition of what is a mathematical structure. To me, this is actually an incredibly fundamental idea, because part of the whole exploration that started by Frege was asking the question, what is the language of mathematics? And Tarski says mathematics is always, there is a kind of a template, how we structure mathematical structures. And it always looks the same way. What is a structure? Always going to be some domain, what we call the domain of discourse. What are we talking about? For example, we're talking about graphs. Maybe the domain is nodes. This is one encoding. Or another encoding, the domain of discourse was graphs and edges. You have to decide what is the domain of discourse. And over the domain of discourse, you're going to have relations and functions. So this is what mathematics is about. You have a domain of discourse, you have relations, you have functions. So when we come back tomorrow, I think this is it, right? We're finishing now. We're going to go back to these questions. Okay, this is a word. First of all, we want to model it as a mathematical structure. So we have to decide what is the domain, and what are the relations, and what are the functions. Once you have this, over this, you now have a logic, first order logic, in which you use the variables refer to elements in the domain, and then you can make assertion using the relations and the functions. In this case, we will not have function, we'll also have relations, also known as predicates. But the first decision is, what is the mathematical structure that underlies a word? And that will continue tomorrow. Thank you.